Okay, yeah. So now that we have discussed both the Hawking effect and the Unruh effect, I'm going to take a little digression now and talk a little bit about black hole temperature. That is, different notions of temperature for black holes. And so we've been mostly talking about this fiducial temperature, which is that which would be observed by a, so we have an observer who is at rest in the black hole rest frame and somehow maintained at rest, then they will see this radiation. And for a Schwarzschild black hole, this approaches the Hawking temperature when you go far away, and then it blows up as you get to the horizon. Now, when you have an ADS Schwarzschild black hole, it also blows up at the horizon, but it goes to zero at infinity because the metric function is blowing up there. So, and if we think about context here, and this is true, regardless of what the actual Hawking temperature is. And Hawking temperature for an ADS Schwarzschild black hole, a large ADS Schwarzschild black hole can have a Hawking temperature that can be arbitrarily large. So we remember that, well, what that means is for the ADS CFT context, if you have a large ADS Schwarzschild black hole, then by that I mean it is above the Hawking page transformation transition. That was 1 over pi L here. So it's then this, we're told in the ADS CFT dictionary, this corresponds to a thermal state at T equals TH in dual CFT, okay? And if the Hawking temperature, as it goes up and, as we raise the Hawking temperature, we're talking about a progressively hotter plasma that we're looking at. Now, the question that I want to think about now is sort of what is the nature of this high temperature state actually on the gravitational side? So is there a sense in which this Hawking temperature, so what does it tell us about observers? What do observers in the Schwarzschild, ADS Schwarzschild space-time actually see? And so the first question I want to ask is the ADS black hole emitting high energy radiation? So we can ask this question. It's got a very high, and in fact, no upper bound on the Hawking temperature that we can find. And then there's a second question that one, so let's call this question 1. Now, we also know that the ADS asymptotic geometry of ADS, it actually reflects back radiation. So the question is, if we are emitting a lot of high energy radiation, then a secondary question is, well, does that mean that the static state that one reaches, an equilibrium state, is that a state where this black hole is in equilibrium with a lot of high energy radiation? So that's the other question we want to ask then. So does this static state describe static geometry, static state, let's say, describe a black hole in equilibrium with reflected Hawking radiation. And so this is, first of all, this is on these black holes, they're on the branch of the ADS. So these are the large ADS black holes. So they actually have positive specific heat. So from that point of view, there's nothing to prevent them from being in, describing to being in thermal equilibrium with an outside reservoir. And furthermore, because the radiation is basically confined by the asymptotic ADS geometry, you could imagine that you could have such a reservoir. But it still seems a bit funny to have this, because when you're doing ADS-CFT, you actually work with a vacuum ADS Schwarzschild black hole solution. You don't work with a solution of a black hole that has a gas of radiation around it. So you might worry that there are some corrections then that you had to take into account. That's a legitimate worry, at least I thought so, enough that I sort of pursued this problem for a while. And now the answer to these questions, or at least my answer to both these questions, is actually no. There is no high energy radiation being emitted, and therefore you don't have to worry about any. And so what I'm going to try to argue to you is that the actual large ADS black hole that's dual to a high temperature thermal state in the dual field theory is actually a very cold and close to just a vacuum solution. So the classical solution should give us an excellent description there. So if you hadn't known that you should be worried about this, you can now stop worrying about it, because it's everything is going to work out fine. But it's a bit of I think it's a little bit of interesting story. Now the question is, how do you describe, so there is a sense in which there is an infinite temperature associated with any black hole. That's for those fiducial observers that are close to the horizon. Now, we don't really think that will lead to we don't think that that means that there is some high, if you think about from a point of view of a freely falling observer, you do not expect to see that. And we're going to confirm that in this computation. And therefore, when you want to think about the semi-classical back reaction to Hawking radiation, you have to think about, well, what is the energy momentum tensor that I should put on the right-hand side of the Einstein equations? It is not going to be the energy momentum tensor that would be appropriate for a fiducial observer. That is the one that you would get in the so-called Bowler vacuum, and that actually diverges at the horizon because, partly just because of this. That would lead to then an infinitely strong back reaction, and you would get that the near horizon geometry should look completely different, should in fact not be anything. The classical limit then would be singular. So if you want to know, I think it's more reasonable that you would normal order your stress tensor, you regulate it and normal order it in such a way as to reflect what would be observed by an observer in free fall. So if you want to know whether there is strong back reaction due to some Hawking radiation, then you should figure out what is it actually that an observer in free fall would see. And then one way to get at that would be to equip that observer with Unruh DeWitt detector and have them tell you what they're reading off. And as I said this morning, in principle, you can do that, but you would need to calculate. You would need to solve this this green function for the quantum field that your scalar field that whose quanta are the Hawking radiation. You would have to solve for the green function along this, so it's pulled back to the world line of the observer that's falling in, and that is a complicated problem. So I'm going to bypass that by using an indirect method. And which also will sort of is I think somewhat interesting in itself. So we're going, yeah. I guess you write out the partition function with the appropriate, you just put beta equal to the inverse of this. Define it in a standard. This is a quantum field theory in a flat space-time with no gravity in it. So there's you just do that in the conventional way. Now, the reason why we liked using these large ADS black holes is because under ADS-CFT, this is a strongly coupled field theory. So, it's hard to do computations reliably on that side. And then the conjecture is that you can actually instead, compute correlation functions using a prescription involving the background geometry. And the concern that I'm raising here is that is a classical geometry with vacuum outside the black hole. And if that black hole was emitting copious radiation, you might worry that is not a good enough description. And in fact, if you are to take one of these black holes in the limit of very large Hawking temperature, and you were to apply the Stefan Boltzmann law to it, then you can actually show that the lifetime of the black hole is extremely short. It is, in fact, you can derive an upper bound of the lifetime. If you just use naively the Hawking temperature formula, that would give you an upper bound on the lifetime, which is basically of order the ADS scale. So no matter how big the black hole was, it would empty itself on that time scale, if that was the right temperature to use. Now, all that radiation would, of course, be reflected back, but you would find then at any given time in this equilibrium, there would be more energy outside the black hole than actually inside it. So that doesn't sound like that would be good news for ADS-CFT, and this is, I claim, is not what happens. So you cannot just use the Stefan Boltzmann law for this. Okay. So we're going to look at an observer in free fall. And I'm going to make it a radial free fall. And we're going to be outside a Schwarzschild black hole. And we want to know what is the temperature that observer measures. Okay. Now, the method I'm going to use is the so-called embedding method. I'm going to embed the space-time, Schwarzschild black hole space-time, into a flat, higher dimensional space-time. I will need a 6-dimensional space-time, I believe, for this. And then I will ask, what is the trajectory? If I look at the word line of my observer in the Schwarzschild background, it is actually going to be mapped into a word line of the corresponding observer or corresponding word line in the higher dimensional theory. And I'm going to interpret the en route temperature of that word line. So I'm going to interpret as the temperature that would be locally measured by this observer. So we'll do this in some steps, and you'll see better as I go along what I mean by this. And so I'm going to use so the question that we want to address is, what temperature does this observer measure? And so we have an indirect answer to it. Okay, we're going to use global embedding method to give an indirect answer. And there are assumptions and justifications that we will see along the way, and I'll leave it up to you to decide, how big a grain of salt you want to take it with. But so I'm just going to give you here an argument, give you a computation, and you will think. And then, of course, a more interesting answer comes when we do the same thing for an ADS-CFT, ADS-Schwarzschild black hole. And then we will see that the temperature using this method that we get for an observer in free fall is radically different from the fiducial. And that is why I'm claiming that we're not going to see any effect to worry about, any major back reaction effect. So the So the steps in this procedure are the following. The first thing you do is you embed black hole space-time. And we're doing this for eternal black holes. I'm not going to try to do this for a evolving geometry. So it's a d-dimensional black hole in general, and we embed it into a flat space-time of a higher dimension. Okay? And in all cases that I know of, it's always, at least one dimension higher, often more. And you can do this for other spacetimes besides black hole. You can take, for example, you're all familiar with this really if you've studied ADS-CFT or ADS geometry. Remember, there's a way to represent anti-de Sitter space, which is to view it as the embedding of a hyperboloid into a higher dimensional space, right? Well, that is just a special case of this embedding. So for ADS-D space-time, you can do this with, you need one extra dimension for this hyperboloid. It turns out that when you do this for Schwarzschild, you need 2 extra dimensions, and if you do ADS Schwarzschild, you'll need 3 extra dimensions. So that's just, and what I'm using here or appealing to is, like I mentioned earlier, last time, was that there's a theorem in Riemannian geometry that says that any curved space I can embed into a sufficiently high dimensional flat space, and I'm going to assume that I can do the same in pseudo-Riemannian geometry for space-times. So, but beyond that, I'm actually going to give you explicit constructions. So we'll simply see these embeddings. We don't need to really worry. I mean, once we have them, I guess we know they exist. All right. And then if I first give you the outline, so this was a strategy that was adopted by Deser and Levin in some papers in around 1998, I believe they were doing this work. And then they were using it really to get at this fiducial temperature. They were pointing out simply that there's kind of a clever and beautiful way that you can get the fiducial temperature using this embedding method. And they tested it for all sorts of different black holes, for Schwarzschild, for ADS Schwarzschild, de Sitter Schwarzschild, Reisner-Nordström, and you name it. Any black hole you could think of, and then you could really do this. And then, but they only used it for fiducial observers. They didn't really want to think about what happened, So then what my student Erling Brynjolfsson and I did 10 years later in 2008, we kind of took this formalism over and we applied it for, so the nice thing about the fiducial observers is that they will be uniformly accelerated observers in the higher dimension, so you can apply the Unruh effect directly. What we did, we said, well, if you're an infalling observer, you're actually undergoing non-uniform acceleration, but if we have the kind of separation of scales that I talked about, time scales that I talked about this morning, you would still say it's meaningful to say I can measure a temperature as I move along, it'll change, and that is what we will see here. But so word line of observer in the original, it basically maps to a world line in the higher dimensional space. And we let and basically we identify alpha r over 2 pi of that, and it's the alpha of it's the acceleration in the higher dimensional space-time that we're going to work out, and we'll identify that as local temperature. In the lower dimension. So it's best just to see how this works in a simple example, and then you will see what I mean here. Okay. So the embedding, I will use the following notation. I'll call it Zi is Zi of x mu, with mu going from 0 to d minus 1. Now d will be 4 for the cases that I'll look at here, but the method is more general. And I will go from 0 to capital D minus 1. Okay? Now, I will view the metric of my lower dimensional spacetime. It's going to be an induced metric in the following sense. I'm going to say that G mu nu is eta ij, and then I have d zeta I x mu okay. And this metric is going to be flat. So this is a diagonal metric of the form minus 1, 1, and then possibly I may have a second negative signature. Remember, when you do ADS, when you embed ADS spacetime into the hyperboloid, you actually have two time directions, right? The isometry group is after all SO d minus 1 comma 2. Okay. Now let me just give you this embedding for, let's take d equals 4, lambda equal to 0, k equals plus 1. Okay, so this is a Schwarzschild black hole, usual one. And the embedding that I'm going to write down was worked out by Fronsdal in 1959. So this is nothing newfangled. This has been around for a while. You have to, in this case, take d equal, capital D has to be 6. And let me just write out what the variables are. So Z0 will be 1 over the, this is the surface gravity, f of r sinh c t. Okay, t is going to be one of my variables. That's my, for mu equal to 0, I'll call that variable t. So I'm going to do this in Schwarzschild coordinates. So xi here, remember for Schwarzschild it's just 1 over 4m. All right. Z1 is 1 over xi root f of r cosh xi t. Okay, so these are two of my coordinates. Z2 is going to be given as follows. I have to do an integral, but I'm integrating a function which is actually manifestly regular, 2m over r squared cubed. Okay, and then Z3 through 5 is just the usual spherical coordinates. Sine theta cos phi, right? Z4 is r sine theta sine phi. Z5 is r cosine theta. Okay, so my Schwarzschild coordinates are t, r, theta, phi, and now I've listed for you the 6 coordinates that are of the embedding. Okay, so this is just an explicit construction here. And now let's first think about a fiducial observer. So that's basically what Deser and Levin were considering. And we'll immediately see. So a fiducial observer is the following. Fiducial observer says that T is going to be tau over root f of r0. So I'm sitting at r equal to 0. R is r0, right? And theta and phi are just they are constant. So this is at rest. That means they're sitting at some fixed value of fixed distance r0 at some angular position, and then you will just have to look at basically T is then related to proper time by this. So tau is the proper time of the observer, the fiducial observer, okay? All right. So this is actually fairly easy now. You can calculate what is the 6 velocity of this observer now. And let's calculate the 6 velocity squared. So that is by definition just eta ij dz I tau dzj tau. So I'm going to basically work through the embedding. So this is the world line of a fiducial observer in Schwarzschild. It maps to some corresponding line, world line in the higher dimensional metric, where basically T becomes a function of tau and all the other guys are constant. So you see it's only the 0th and the first. For the fiducial observer, it's only the 0th and the first variable that are actually changing time. And you can do a quick calculation here. You take your derivatives there. This is going to give you a cosh times xi. The xi cancels out. And then you have the chain rule will give you a 1 over root f of r0. That cancels this guy. And so you see when you do this, you're actually going to get -1. So that is what you want. That is just telling you that this is a standard affine parameterization of a world line of a time-like observer here. Okay? But now I can do another calculation, which is I can calculate the 6 acceleration and square that. And that gives me, now I have to take second derivatives with respect to the proper time. And now I have to do a little bit of algebra, but not much. And you can easily check that you're going to get that this is xi over 2 pi, especially if I put 2 pi here. So I want to do this with a 2 pi here simply because it's the en route temperature of this guy. So let's call this is T en route in the 6 dimensions squared, right? Well, okay, let me wait with that. Let me just calculate this. So it's square of this guy is going to be xi squared over f of r0. It's not too hard to see. When you do another derivative, you bring out a second time. So now this has become cosh when you took the first derivative. It becomes sinh again when you put xi comes out. So now I will have overall xi in front, and I will get another square root of f from the, and once you do all of this, you will end up with this expression here. And this tells you that T en route from the 6-dimensional point of view, which is alpha 6 over 2 pi, is then exactly the fiducial temperature at R0. Okay. So this pops out rather neatly from this. And then you can do this radius. In fact, this works for any of those static geometries. Well, you can do this radius, which I'll show you the embedding in a minute. But now let's think about an observer in free fall. Okay? So we're going to think about an observer who's in radial free fall. So for that, we need to do a little bit of computation. So now we're going to look at an observer in free fall. So we have to solve the radial for the radial orbit. So we do this in Schwarzschild coordinates. We want -1 to be equal to u squared. So that's equal to minus f dt d tau plus 1 over f dr d tau, right? This is the 4 velocity now. Maybe I should. So I used a capital letter for the 6 velocity in the higher bedding. So now I'm just going to solve for the, and you know there's going to be a conserved charge because the metric doesn't depend on the time. We can write minus E is GTT dt d tau, right? This is just standard. So it's the, you have to think about the conserved momentum has a, with index down, should be a constant, so that's this guy. And I can take these two together now, and that will, I will get the following for the orbit equation. So we're going to do the free fall towards the black hole. We're going to find that dr d tau is then minus f of r 0. Okay, I guess I'm skipping a step here. Let me do that first. Let me plug this back in up here. So this tells me that dr d tau, I can isolate that. I can eliminate the dt d tau using this equation here. I can use that gtt as minus f, and I end up with this expression here, that this is equal to e squared minus f, right? Now, how do I think of this? Well, this, of course, is the one parameter family here. That depends on where the turning point is of this orbit, right? So what I know is that this is equal to 0 at turning point if E is equal to f of r0, okay? Here? No, it's f. You put this guy in here, you will have an inverse. So this guy is minus f. Cancel one of them, this guy goes up. So this is the minus f is when you multiply it here, okay? All right? So this is the orbit equation, and dr d tau is going to be 0 if these two things agree. Okay, so I'm going to say I have a turning point at r equal to r0. That means that E is actually equal to square root of f of r0, right? So that's going to be my turning point. So that what I'm thinking of here is that if this is the r direction, here is RH. I start with my observer here, and I simply let it go. So at some time, I'm at r equal to r0. I drop this guy, and then it'll start accelerating towards the black hole, the free fall towards the black hole. So this is always going to be the case, that just saying that you have somebody in free fall is not enough to determine, you have to say where was the drop from. So, but anyway, this is what we have. Okay, so therefore, The solution, the equation that I want to solve is dr d tau minus square root f of r0 minus f of r. And this will give me the orbit for a given value of the turning point. All right. So now I'm actually going to write this as minus square root of x minus x naught, where x is just defined as 2m over r. That's just convenient. You'll see this guy is 1 minus x naught. This guy is 1 minus x, so that's why you get x minus x naught here. And then I can write this as dx d tau is equal to x squared over 2m square root of x minus x naught. And then dt d tau, which is what will come into my calculations as well, you can easily see is e over f. And so that's equal to square root of 1 minus x naught divided by 1 minus x. Okay, and x basically goes, if I plot with x here, x equal to 1 is, here's the event horizon, this is r equal to rh. And then this x equal to 0 is r goes to infinity. Okay, so I'm interested in things as a function of x from 0 to 1. Okay, so this is my orbit. And now what I want to do is I want to solve these orbit equations. I actually don't need to solve them, I just need to plug them in when I calculate. So when I, remember, when I calculate my sixth velocity, I need to calculate this derivatives with respect to tau. Now I have two things that are functions of tau. Both the time, d tau is a function of tau, and so is this. So I'll use my chain rule, but every time I see a derivative with respect to tau, I can replace it with this x variable here. Okay, so let me do that. Actually, let me not do that. But you can see what the principle is. Now, it's going to be more complicated than before because all of these guys are functions of r. So now I actually have to calculate, when I calculate this thing, I will not just get a contribution from the first two values of I and j. I have to sum all of them, right? And then I have to take two derivatives. So you get a rather complicated expression here, but this is just it's a prescription. You simply just do the computation. It's not, it's straightforward, but tedious. I guess this is what we write in our papers when we don't want to write things out. Okay, so let me just tell you what the answer is. Now, of course, as I said, just saying that you have an observer in free fall is not quite enough to uniquely determine it. So what we decided was to focus on a particular class of observers. So we're going to think about observers are, you see there is a preferred frame. The rest frame of the black hole is a preferred frame. So we want to think about observers who are in free fall, but who are also at rest momentarily. And it's precisely observers, you can imagine they're observers who are at the turning point. So basically you think of an observer, we've been holding them there for a while. Now we're going to do our measurements, so we let them go, okay? And they start falling towards the black hole, and those are the observers that we want to focus on. So basically so I want to think about an observer in free fall at rest. So they're at their turning point at r equal to r naught. So, and then what we did is we made an acronym. It's always important to have a good acronym. And so the temperature that we're going to calculate is the free fall at rest temperature. Okay? So, and this is just a prescription now. I'm going to take my 6 acceleration at r0, divide by 2 pi, okay? And so when I do this computation here, of course I have the orbit equation I solve for arbitrary values of r. for a given orbit. And now what I want to do is then plug in r equal to r0 in that orbit. So then I know that I am at rest. So that simplifies things a lot. And you get an amazingly simple answer here. You get c over 2 pi. That's already a good sign. You get 1 plus x0 plus x0 squared plus, so that is the end, where x is this variable here. And x0 is the one where I evaluated at the turning point. Okay? So this is telling me that if I'm calculating, so let me plot this as a function of r now. Okay? So r goes to infinity, that's x not going to 0. You see rather a nice result. We get that it approaches the Hawking temperature far away. Now that, I think we should be happy with. You look at what happens when I go all the way to the horizon. So this is r equal to RH. Well, x naught is then going to 1. And so you get square root of 4, which is twice the Hawking temperature. So you get just this uniformly. So here's the answer. Okay? And in particular, that this guy, as r0 goes to RH, is twice the Hawking temperature. This is finite. Remember, the fiducial temperature was actually blowing up there. Now, little caveat here. The important thing is that it's finite and that it has an order 1 coefficient. The precise value of this coefficient actually has limited operational meaning. And why do I say that? Well, let's think about this observer. The observer is falling into the black hole. How many of you remember what is the upper limit of the proper time remaining to an observer who enters a black hole in free fall? Well, it's of order the light crossing time, right? It's pi times the Schwarzschild length in the appropriate unit. So what we know is that whatever this observer is going to do, it's being dropped very close to the horizon, so it's going to pass into the black hole. Now the temperature measurement, how long does it take to measure a temperature that's of order TH? Well, that temperature has a certain energy scale, right? There's a thermal wavelength to it. And so if you're going to measure a temperature of order T, you need a time of order 1 over T, right? To do it, the precision. And that is actually the same length of time that you have before you hit the singularity. And of course, even before you hit the singularity, you're rather dramatically changing your environment. So what I'm saying here is that, okay, it's nice that this is finite. The fact that it's 2 and not 2.4 or 3 is actually not that important because this is not going to be a precise measurement. Okay. Okay. Yes, 2m over r. So it's RH over r more generally. Okay. Yes. So this was the Schwarzschild case, but now let's think about ADS Schwarzschild, where the Hawking temperature can be quite high. Yes. Get one as well. That's the first thing you do. Yes. That is kind of a check, and yeah. That's reasonable. Actually, I could have done that. That's only a little bit of, it's a little bit instructive to see how that works, but it's not instructive enough that I wanted to take 10 minutes to do it. Then the acceleration computation is actually more than 10 minutes. So, but it is very straightforward. So it's nothing. It's just a question of not taking time to do it here. All right. So let's now do ADS Schwarzschild, and I'm going to do even less details there. So what is the embedding in that case? Now it is tempting to reuse some of it because of course we're doing spherical symmetry, so the actual Z3, 4, 5 are going to be unchanged. But let's so ADS Schwarzschild, we're going to do D equals 4, the less than 0, K equals 1, okay? So that's ADS Schwarzschild, all right? Now, capital D in this case is 7. So we need one more direction now. And eta ij in this case is going to be diagonal. It's going to have a minus 1, 1, 4, 5, 6. Yeah, so like that. Okay, so it's going to have two time-like variables. And now it starts out very similar to what we did before. Z0 is going to be, again, it's xi root f of r sinh. So this part is the same. Z1 likewise is cosh. And the rest is only going to involve the r, the space-like variables. But things are more complicated now because we have basically now two parameters. We have the length, the ADS length is also now. We have the area, we have the RH, so the value of the radial variable at the horizon, and then we have L as an independent parameter. And the large black holes have RH large compared to L and vice versa. But these formulas cover both cases. Let me just write this out. It's not maybe terribly illuminating. The point is that it's a well-defined expression. You get some constants out in front here, like so. You again have to now do an integral. And you get, there is some method to the madness here, but the important thing is that this is a perfectly regular function here. RH squared plus L squared. So that's this guy. Z3 is R sine theta cos phi. Z4 is R sine theta sine phi. And Z5 is R cosine theta. And now, of course, the seventh guy is going to be a time-like variable. That's Z6. It's got some coefficients in front. L squared plus RH squared. L squared plus 9 RH squared. I don't know, really don't have any insight into where these numbers come from, but it's what you get. So this is the thing out front, and then you integrate again. And because we're taking derivatives of these, it doesn't really matter where exactly we put the lower range here. And then we have the following integral. It's not too dissimilar from the other one, slightly simpler actually. Important thing is this just a concrete, and this is not, this embedding was worked out by Deser and Levin. And then they checked that they would get the right fiducial temperature and all from here. But then we can use this now to think about an observer in free fall. Now, the orbit equation is more complicated here, but we can still do it. I'm not going to go through the details. But the thinking is the same. We think about an observer who is dropped from rest. So we're going to calculate again this temperature, which is for an observer in free fall who happens to be at rest. Okay? And let's see what we get. Well, let me not write it out. It is actually a fairly lengthy expression, but I'll show you some limits of it. Okay? Yes? How do you get them? You look them up in a paper by Deser and Levin. No. You get them by basically by working backwards from saying, right, so the metric is, you basically work backwards from the induced metric expression. You integrate your way back from that. Yeah, that's right. You basically, you kind of start with these two and then you see what you have to do, what you have to complement them with to avoid any singularities in the embedding. So it's a little bit of, it's a while since I was doing this, but it's not entirely algorithmic. You have to sort of follow, you can follow your nose to some extent, but then you have to make some choices. Now, of course, this bit here is at 3, 4, 5. That's immediately follows just from the spherical symmetry. And then, yep. No, it's regular at r equals to, there's nothing, no strong extrinsic curvature happening at when you get to the horizon. Of course, the intrinsic metric is going to have a curvature singularity at r equal to 0. That's a feature. That's not a bug. That it must have that, right? Okay. So the first thing you do is you check that your 7-dimensional velocity squared is actually -1. That means just that you've solved your orbit equations correctly and your embedding is consistent. So that was the first thing we did. And then you calculate your A7 squared, so the 7 acceleration, and you get some expression. And then to get your temperature for a free falling observer at rest, actually I'm going to express this as a function, squared here, is going to be 1 over 4 pi squared then, A7 squared, evaluated at r equal to r0, okay? And the answer that we get is, first of all, you can write out just by dimensional analysis, you're going to have 1 over L, and this appears like this, L squared, sorry. F, so the units of acceleration are going to be 1 over length because the way, the 7 velocity is dimensionless. And then I just have some function that one has to figure out. Its function, I have expressed it in terms of these 2 dimensionless variables. X is, as before, x naught is just RH divided by R naught. RH is where you're at the horizon. R naught is where you drop, okay? And C is just a dimensionless variable that tells you whether you have a small or a large black hole. C goes to 0 is the limit of planar black holes. C goes to infinity is the small black holes. Okay, so and now let's look at some properties of this thing. Okay, so in particular let's look at what does this thing do far away. Let R0 go to infinity. So we're dropping the observer asymptotically far away from the black hole. So what do you think we should get there? Well, it should reduce to what you get when you're just in ADS spacetime, right? And sure enough, what you will find is that this function just goes to -1 or -2 maybe. This goes to -1 over 4 pi squared L squared, okay? And what this is telling you is that A7 squared is actually -1 over L squared. Now, you might pause at that because One of the things that you learn in GR class, maybe even in special relativity class, is that the acceleration is always orthogonal. The for acceleration is orthogonal to the for velocity. For velocity is always time-like. And so in ordinary Minkowski spacetime, that means, of course, that this guy has to be space-like, right? But the different thing now is when our embedding space has two time directions, that's no longer guaranteed. So you can actually find a time-like acceleration vector that is orthogonal to the, and this is exactly what happens here, is that this guy is actually, its square is negative. But this is actually what you want, because if you think about it, if I am just think about empty ADS spacetime, no black hole, and I put a geodesic observer there, so some observer sitting somewhere. Now they should not be seeing thermal radiation, right? They're just at rest in ADS somewhere. And the way this formalism takes care of that is by saying, well, okay, from that point of view, this acceleration squared is negative, so it looks like their temperature is just pure imaginary, and we conclude from that there is no thermal radiation. And in fact, I'm not going to go through it here, but it's true that if you have an empty ADS spacetime, and you just think about the Unruh effect in anti-de Sitter space instead of in Minkowski space. When we had the Unruh effect in Minkowski spacetime, we got a temperature that was proportional to the acceleration, right? What we find in anti-de Sitter spacetime is that if you have a small acceleration, there is no thermal, the observer does not see any thermal radiation. The observer only sees thermal radiation if the acceleration in these units exceeds the ADS scale. So this is now the acceleration in the, if you're just doing anti-de Sitter, four-dimensional anti-de Sitter space, uniformly accelerated observer sees only an Unruh effect if the acceleration exceeds the ADS scale, okay? Basically, it's bigger than 1 over L. Now, if you do that computation through this, if you look at a uniformly accelerated observer in empty ADS, you can go through the same sort of embedding story. It's simpler there. You all know this hyperboloid embedding. Then you will find that exactly when the, where the four-dimensional accelerated observer, when their acceleration gives rise to a finite temperature, that is exactly where this will cross through zero. So where the higher dimensional acceleration, so we've embedded ADS space into some higher dimensional flat space, and when the uniformly accelerated, the world line of a uniformly accelerated observer in ADS is actually also an accelerated observer in the higher dimensional flat space-time. And the fact that you don't see an Unruh effect until you pass a certain threshold acceleration is precisely the fact that the corresponding high dimensional acceleration will be time-like below that level, and only when you have sufficiently accelerate sufficiently rapidly in the lower dimensional space, then this flips around. Okay. So this is, yep. Yeah. No, I'm not, I think we can talk about that afterwards. I don't think that's quite right. So, I mean, this embedding, like it or not, has already been found, and we're just going to use it. Let's take it out, right? And yeah, so let's not worry about that. But you do actually need them all for these kind of observers that we have, because these all actually involve R, and R is changing for the guy who's in free fall. So we are going to drop them from rest, but we're going to calculate their acceleration, which means that we really need an expression that would allow us to. You need the function for all of R to be able to take its derivatives. That's right. Yeah. We will see. Look, this was just the first observation. When you're far away from the black hole, you shouldn't see any radiation because you're just in ambient ADS space-time, and that's indeed what we see. And this is the interpretation of it, is that when this is time-like, there is no radiation. Now let's ask what happens if we go in the other direction. We go towards the black hole, okay? And so R0 goes to RH. And then you find that it actually goes to 1 over 4 pi squared RH squared. So the only difference is that the sign flips and the L becomes an RH. That's just what you get, okay? And this is positive. Yes, absolutely. Okay, so now it's space-like and it looks like you actually have. And let's think about what is the actual temperature that we have. So let's just remind ourselves what T Hawking is for these guys. T Hawking is 1 over 4 pi, right? And I think, therefore, this should have been like this. I think I may have simply done this. And then we have, no, I'm not going to have to remember, there's a 3 in there somewhere, right? There's a 3 RH over L. Okay? And what you're finding is actually that in the limit that, no, and this was actually correct. This was, as it was before, was correct. Pi squared over. So indeed, if you let C here go to infinity, L goes to infinity, this term would go away, then you of course should approach the Schwarzschild value. When your cosmological constant goes away, and this is the Hawking temperature in that case. You take square root of this, it's twice that. So we get back the Schwarzschild answer in that case. So that is working as a limit. But if I take a large ADS black hole where this guy now is dominating, and for a large ADS black hole, this is the thing that grows, you'll notice the free fall, this guy is actually not growing at all. It's getting smaller and smaller. Okay. And this was my point, is that the observer in free fall will never actually see a high temperature, even though, in fact, the bigger the black hole, the lower the temperature is that they see. Yes? Not remotely. But how about that? Is that better? Thank you. Yeah. So, actually, let's look at this a little bit more, slightly more detail. You might think that you have something like a thermal atmosphere here, that you have. It's actually a positive value close to the black hole. It's a negative value far. Now, there's a theorem you all learned in calculus. I think it's Bolzano's theorem that says if you have a continuous function that's positive one side, negative, it must have a 0 somewhere on the way, right? So that is indeed what happens here. Of course, theorem doesn't tell you how many zeros, but it turns out there's only one in this for this function. And so if I show you what this thing looks like, it's going to be let me just give you here an expression. I'm going to plot for you this guy squared over T Hawking squared. And I'm going to do it on the one hand for a small black hole, and on the other hand, I'm going to do it for a large black hole, okay? And remember, x1 is the horizon. And then, so if I have a small black hole, this guy at the horizon will be 4 times the Hawking temperature, right? Right? So I start out here somewhere. And then it used to go just to the Hawking temperature if it was a Schwarzschild. So Schwarzschild would do something like this. And what the small black hole will do is it'll stay like this for a long time. But then eventually it'll remember that you go sufficiently far away from the black hole that it's the ADS space picks up, and then you'll get the negative answer that I had before, right? So that's what it looks for a small black hole. Now this is very reasonable because this is a black hole that's just being embedded in some ADS cosmology, with the cosmological constant being tiny, and and the ADS length scale therefore very large. For a large black hole, what you're going to find is that at 1, you're going to have this answer which is not very large because it's going to go inverse to this guy, but so it's going to be much smaller than but let me just, for the sake of argument, so that I can actually do this one actually will do something like this. Okay? And so there will be this region close to the horizon where I actually have a positive value. And then you might say, well, isn't that just the region where I have an atmosphere of, Hawking radiation that's bouncing back and forth, and it's just being, reflected back by the ADS geometry. That's a nice thought, but it's actually probably not how it works, because if you think about it, so let's actually do a little estimating here, and so if you have, for a large black hole, this guy is actually greater than 0 in a fairly thin layer, in a near horizon layer. And this, to give you this answer that I'm going to give you, I actually need to know what that function f is. It comes from analyzing that. I didn't write it out for you. It's like half a page expression, so I'm not going to try to even reproduce that. But you find that there's a layer of proper thickness. So basically, I want to know what is the proper distance between this point where the thing turns negative to here. Let's call that d. And what you will find is, and approximately you will get that this is 2 times root 2 over 3 L over RH times L plus corrections. So when RH is large compared to L, this thing here is going, is a number that is small compared to the ADS length. Okay? You're getting for a large ADS black hole. Now it can still be a macroscopic distance if this guy is maybe 1 over 100 and this guy is many light years. So that's not. But the point though is that what this says for me is that D is much less than L if RH is much, much greater than L. And in fact, D goes to 0 in the planar limit. Now that's already encouraging because most of the ADS-CFT applications we do is for planar ADS black holes. And literally for those, we would say there really is no radiation at all outside. Okay. So that's telling us that we were extremely well justified in using the classical expression. There really is no radiation to lead to any back reaction. Okay. So an observer in free fall outside a planar ADS black hole will simply not see any temperature. Okay. So that's good. And yet, the dual description in the CFT is, of course, that of a thermal state. There's no contradiction there. It's a different, that is a dual theory, which is not a gravitational theory and is just, describing some high temperature plasma. However, we can ask, what is the thermal wavelength of the of the actual radiation that you would see. Well, that's going to be determined by so we're finding here a free fall temperature which is going like 1 over the radius of the black hole. So that is going to have a wavelength then that is of order RH, right? So the thermal wavelength, lambda, is 1 over, which is RH. And that in turn is much bigger than L, which in turn is much bigger than D. And so we're trying to fit thermal radiation into a box which is much, much shorter than that is something that we know that engineers call impedance mismatch. You really can't do that. There is no room for them. There's a little bit of energy in the field here, and you would call that actually, it's called an evanescent wave, right? And so there's no propagating radiation. All right. So we would conclude then that an observer in free fall outside a large ADS black hole doesn't really see cannot measure thermal radiation. Okay. This means we expect a vanishing back reaction to the Hawking effect in this case. Now, this is something one can do. You can do, again, to get back reaction, you have to do some sort of two-dimensional approximation. So you can do a back reaction computation sort of when you focus on only the S-wave sector of the Hawking radiation. This is sort of a standard thing to do. And you indeed find that there is not any strong back reaction. So that is consistent with this. Okay. Now, of course, ideally, what you would want to do is to confirm this by doing the computation with the en route DeWitt detector and having them, switching it on for appropriate periods of time and just checking that you actually don't see anything falling into a black hole. But that's a much harder computation. So this is a calculation I can do. The other one is not. All right, and I guess we didn't take any break yet. Why don't we take a short break now, and then I will spend the last 20 minutes, right? I will do something completely different. I will start setting up how you would imagine doing an effective field theory approach to black hole evolution. So you want to really we want to at least qualitatively start taking into account what happens for a Schwarzschild black hole in asymptotically flat spacetime when that starts evaporating. So let's take a 5-minute break, and then we'll go on for another 20 minutes to set the scene for tomorrow. So these are nice toy models. You can be extremely explicit. You can find eternal black hole solutions. You can find black holes that are formed in collapse. You can have arbitrary incoming matter distributions, and you can figure out the solutions. Those are just at the classical level. But then what CGHS, Callan, Giddings, Harvey, and Strominger did was to say, well, we also know, so they had very simple matter. They had conformal fields in 1+1 dimension, just massless scalars. And they argued that you could include the one loop effect of those scalars by adding what's called the Polyakov or Polyakov-Liouville term, which is a non-local term that you add to the action. In 2 dimensions, you can actually work in conformal gauge where that term turns out to be local. And then you can keep going, and you can actually put this as a right-hand side, include this term, and then that will give you semi-classical corrections that can be studied. And that's an interesting story, but I think I will put that off, and we can do some of that story tomorrow if there's any time left over. I think I want to talk to you about a more interesting story, which is how would you even try to do this in 3+1 dimensions? And let me emphasize that we don't really have a semi-classical set of equations here, but we have a pretty good notion of how this should work. And so let's talk about black hole evolution. Okay, and what I have in mind here is to do this in 3+1 dimensions. And I've already drawn for you the Penrose diagram that we anticipate. And this is one where, we form the black hole, but then the black hole will actually evaporate, and therefore the diagram is something like this, right? Here could be the infalling matter, could be a star, could be a shell or whatever. We form our black hole, but instead of the world ending here with a black hole around forever, there's going to be some Hawking radiation that comes out this way. We conclude that we basically, that's a conclusion we draw from the Hawking effect that we discussed earlier. And then the black hole will gradually shrink. Now there will be some question marks about what exactly happens here. Then clearly the black hole has become so small that we can't really trust the computation that we were doing. But if we start with a very, very large black hole, most of its lifetime, this very long lifetime, we can actually follow the story. And there should not, if we're thinking, for example, in terms of unitary evolution, about the information that the black hole contains early on, if we're really going to entertain the notion that that information returns back to infinity, it really has to have returned before this. Otherwise, you would be left with some remnant, and there are issues with remnants. I'll talk to you about that more tomorrow when I've posed the information problem and we have start discussing possible resolutions. But even if we had a remnant left behind, this would just be the word line of that remnant then. So it's the same diagram. Okay, so now in this diagram, this would be r equal to 0. And so once the black hole is gone, we'll be back to r equal to 0 here. And there's here sort of a last piece of, so when the final, what it was, 10 to the 6 kilograms of black holes evaporate in 1 second, you'll get a burst of high energy radiation that comes out here. And that's going to be what we call UE, which is the end point of the black hole. So this is once past this, if you're at very late times, the black hole will be gone and all the radiation will have passed outside you. Okay, so that's the picture. Now, and like I said, we want to describe this evolution. Now, to have a complete description, we need a theory that describes the physics of the matter that's undergoing gravitational collapse, right? And then we're going to couple that to to gravity, and so therefore we will, a classical back reaction of that matter is the formation of the black hole. And then that theory should also be able to describe the slow evaporation of the black hole. Okay. So we want to describe the evolution of matter and the geometry. Including back reaction effects. So that's the goal. So in particular, we want to be able to follow how the black hole shrinks. And this is going to be a pretty much an adiabatic process if we have a large black hole for a very, very long time. And then, so the question is, can we have some theoretical description of this? And what you would need is basically, and the expectation is that this is going to be governed by what you would call an effective field theory. And so what are the ingredients in that effective field theory? Well, we know some of them. The Einstein-Hilbert part is what we've been talking about. That's the classical gravity. We can put the standard model. That's our matter. Maybe there's some exotic matter you want to study. You can do that as well. Okay. But then it gets more tricky. What else should we have? Well, as I mentioned in the first lecture, you would expect there to be a set of terms sort of increasing dimension so energy dimension, and there would be something like this. All possible ways of contracting the Riemann tensor with itself, mu nu lambda sigma. This is the Kretschmann scalar. And there could be covariant derivatives of R. There can be also terms that involve curvature couplings to the matter that we normally drop when we do the standard model physics. So those should all be there as well. And in effective field theory, we would arrange this in some high, and this is of course only schematic, what I'm doing here. And then you could even imagine that there are also terms that go like R cubed. And those you would have, I'm going to divide here by an omega squared, and omega is a cutoff. So when you define an effective field theory, you always have in mind that there is a cutoff. This theory, of course, when you include all these high dimension terms, is not going to be renormalizable. It's simply an effective description of some more fundamental theory that you have at some given, up to some given energy scale. Okay? So it's a cutoff energy scale below which this effective field theory is valid. Okay? And you basically would be instructed to include all possible terms that are consistent with the symmetries of your theory. Because once you start, if you start with some fundamental theory, you start doing renormalization, regularization, you will find that your renormalization group flow will generate all possible terms, even if you didn't put them in to start with. So this is clearly not a particularly simple thing to work with. And as I said, we don't really have a concrete example of such a theory to work with, but we're simply going to make the assumption that this can be done in principle. And we can ask sort of, how much should we worry about these higher order terms? Well, those will be suppressed. The higher their dimension, the more they'll be suppressed by the cutoff. Okay, so we can, but unfortunately, we know that our quantum theory does involve massless fields. And so we have to be mindful of that. Actually, when we do that in our effective action, when we integrate out, if you like, some massless field, local terms. So what do we do with those? Well, I guess we have to include them. So these give rise to non-local terms. In the effective action. But we can actually deal with those by introducing some auxiliary fields. To obtain, again, a local action. Again, maybe the simplest example is in lower dimensions. This Polyakov term that I mentioned. So of course that is a very special case, but let me. So Polyakov-Liouville term in 2D gravity. So there you imagine you have some massless fields, you've integrated them out, and that term is going to look something like this. Let's say that your fields are just those of a conformal field. It's a two-dimensional theory. Let's say the matter theory is a conformal field theory with conformal anomaly C. And I'm just showing you how one sort of proceeds. And then you would know that this guy is non-local, so I have a d squared y minus gy. I have a d squared y prime, gy prime, and then this particular term looks something like Ricci scalar evaluated at y, and then I have a propagator, basically a green function between y and y prime, Ricci scalar at y prime. So some of you may be familiar with this. And I can always render this local by, I can introduce scalar z with, roughly speaking, this is going to be, I forget the numbers out front, they're not so important. I just write this as d squared y minus g. And then I will have just a standard kinetic term dz squared plus some number times r times z. If you think about it, if you integrate out this z, you're going to get precisely a term like this. This kind of looks like a source term, right? And so when you integrate this guy out, you are going to get the inverse propagator, which is the green function. So this sort of thing you can do in higher dimensions too. It's more complicated, but it's in principle can be done. Okay, so this is just as a, and this is in fact exactly what the term that Callan and company introduced in their CGHS model to get their quantum effects. So who knows? Maybe we'll get there tomorrow. We'll see. Okay. Now the detailed form of this effective action I'm not going to be so concerned with. Effective action for 3+1 dimensional gravity is really not known. But we can still, but we know that higher order terms are going to be suppressed. So provided if basically, I'm going to put quotations around here, the size, the strength of the curvature, how do you measure that can be a little bit tricky, but it has to be small compared to just dimensionally. Now, the reason I do it this way, you can't just say, for example, the Ricci scalar here, because for a Schwarzschild black hole, a Ricci scalar is 0, even though arbitrarily close to the singularity. So one thing that one often works with is this Kretschmann scalar, which is r squared with all indices contracted. And so you want this to be small. So let's just look at as an example. Let's do Schwarzschild black hole. Of 1 solar mass. And let's make our cutoff scale to be 1 TeV, like we would do in particle physics these days. Okay? Omega is 1 TeV. This is just to give you a sense. Then if I calculate my Kretschmann scalar at the horizon and divide now by omega to the 4th then, because it's 2 powers of the curvature here, I do this at r equals to RH, and I find that this is about 10 to the minus 44. So I would probably be perfectly sanguine to use this effective field theory then, by dropping terms that are suppressed by factors like this. Okay. Now, we're going to work on a background space-time that looks like this. And so this means that we can be sure, let's say, as we said, as long as our Cauchy surfaces stay away from this region here, close to the singularity, we're assuming that we have a large black hole when we form it, then curvature is going to be low here. And I should be able to use my effective field theory, on some Cauchy surfaces that keep going, just as long as they stay away from this region. And one has to be a bit careful, of course, because this is a Penrose diagram, and there can be distances are a bit deceptive. It's the causal structures that are well, but certainly as long as they intersect this horizon, long before the black hole has shrunk to anywhere near the Planck scale, we should be fine. But there's a further condition that we need on our things, because this is just about the ambient curvature here, but we had better not have singular Cauchy surfaces. We better not have strong extrinsic curvatures either. So that's going to be a limitation as well. So let's think about that. So the extrinsic curvature of a Cauchy surface must also remain small. Okay, compared to the cutoff scale. That seems like a reasonable condition. And then what we're going to do is we're going to assume that we have constructed somehow this effective field theory that describe this, right? And we're going to define it on a set of Cauchy surfaces that satisfy these conditions. They stay away from the strong region for as long as the curvature region, and we are not allowed to do that by, abruptly making abrupt changes locally, sort of to embed them in a weird way. So it has to be and what this leads you to is a construction of what are called nice slices or nice Cauchy surfaces. And this was a term that was coined back in the 90s when people were there was a lot of interest in understanding these semi-classical models, because back then people were hoping that maybe they could actually capture, sort of be a first step in some very systematic description of, towards doing quantum gravity. And I would say its necessary condition is to have a reasonable semi-classical description. But what we'll see tomorrow is that what is interesting about the information problem is that usually when you have an effective field theory, its breakdown, it kind of predicts its own breakdown. It breaks down when your curvature becomes strong or your extrinsic curvature. So that's usually how we know that an effective field theory is not going to lead us astray. What the information problem tells us is that we can actually formulate it on a set of Cauchy surfaces, and we can lead to contradictions without the effective field theory is actually claiming that it's fine. And it simply tells you that you make certain predictions based on that effective field theory, and then either those predictions are correct, and unitarity is not a feature of the real world once you include gravitational interactions, which is what was Hawking's conclusion, or the effective field theory is breaking down for some subtle reason that's not obvious, and which is what I think most of us would agree is. And so what I'm going to do today, just before I end, is just do a very simple construction of these nice slices, and then tomorrow we'll start talking about the information problem. So let's just do a very simple construction, and not for this background because that's kind of a little bit harder. Simple construction for eternal Schwarzschild black hole. Okay? And we're going to do this in Kruskal coordinates, because then I can talk about the whole geometry. But the Kruskal coordinates are better than the Penrose diagram because they are not quite as deceptive in terms of distances. So let's just remind ourselves what the black hole looks like in those coordinates. And then we can write down the expressions that we want. So remember our Kruskal diagram. Before we did the last, it looked like this. I had these null directions. I had the capital V out here. I have the capital U out here, right? I have my singularity at U times V equal to 1, right? I have the horizon, you know, and then of course I have another singularity down here, but we're not going to be so concerned with that. And so how do I do my construction? Well, the first thing I do is to find a constant R surface inside here. So I'm going to find, and they look like hyperbolas. So it's a UV equals constant, but I'm going to make it to be UV. UV is equal to alpha squared, which is less than 1. And in particular, if I want to stay away from this, this needs to be, you know, a number that could be a half or something like that. It has to be, it's not allowed to be very close to here because the curvature, and in fact, you can dictate how strong is the curvature on the surface simply by picking this alpha here. And so my first surface, I'm going to take this here at this symmetry point here, and I'm going to attach it to this thing here. This is the surface I'm going to call t equal to 0, okay? And the t equal to 0 slice is the following. It is Vu equals alpha squared if V is less than U, right? That's in here. V is less than U, that's this part of it, right? And then I'm going to do a smooth join onto this straight line here. And I'm going to say that V plus U is 2 alpha if V is greater than U, okay? And then, of course, I will, you know, smooth the join. How, you know, I will, we can certainly make a little bit more careful junction here that can have arbitrary, it can be differentiable as often as you need. Okay, that's certainly something we can do. So we want to have join at V equals U smoothed precisely to avoid the second condition, to avoid strong extrinsic curvature. So this is time equal to, so you see what's nice about this slice is that it certainly stays away from the, but it comes out of the black hole. So I can label it, and this T here is really, I can use the Schwarzschild time asymptotically here, just to label the slice, right? But it's not a Schwarzschild slice because those go, constant Schwarzschild time slices they all emanate from here, and they're time degenerates here. T equal to 0 is also true here in this slicing. Okay. Now, how do I move to different T's? That's simple. I'll simply say that Vu is equal to alpha squared if V, instead of being less than U, is less e to the t over 2m, right, times U. And then I will write e to the minus t over 4m V plus e to the t over 4m U is equal to 2 alpha if V is bigger than this. So what am I doing here? So I'm actually just, let's say t is bigger than 0. That just means that I stay with this here a little bit longer until I get about here. And then I get this curve here. So this is a t greater than 0. And of course, it's going to be parallel to a particular time slice over here. And that's what we use to label here for the Schwarzschild time. So we use, when it's horizontal and it's parallel to this one, that's when we call it time equal to 0. And so it's really the slope here is what's telling us what is the time variable here. So these are time slices. And of course, I can do t less than 0 as well. So now I have a whole family of slices here. And they have rather nice features. So imagine some infalling particle that starts from rest here somewhere. Okay. Now this infalling particle, if we choose alpha to be fairly small, so we're out here somewhere, is going to intersect this slice. So let's say I drop it here, it's going to go this way, right? It's going to intersect this slice as a low energy observer, right? It's, I'll drop this particle, it'll have low energy. In fact, what I can say is that infalling particle if it starts from rest, near the horizon, what distinguishes this from the Schwarzschild slices is the following, is that if I calculate the 3 momentum of this particle in Schwarzschild coordinates, it actually diverges as I get closer to the horizon. It diverges as r goes to RH, okay? Whereas 3 momentum remains small. In the local rest frame of a nice slice, okay? So basically what this construction does for you is to get you through the horizon with without anything, anything bad happening to your coordinate system. But there is, of course, something going on here, which is that because these slices are not Schwarzschild time slices, the generator that, generates time translations from one nice slice to the next is actually going to be a time-dependent Hamiltonian, right? Because, the time translation generator here is not a killing vector. Asymptotically, if you're very far away, it gets very close to being a killing vector. But here it's not. Okay? Now, what happens when you have an effective Hamiltonian that is time dependent? Like this one will be near the black hole. Right. And actually, you get particle production. Right. So from this point of view, if you have an effective field theory on these nice slices, okay, and this will be the last thing that I write here, is that I can, I can offer this as a very qualitative derivation of the Hawking effect, really, because let's say I have my effective field theory Hamiltonian, I've rendered it local, and then I have this effective field theory. Now I wrote down, of course, an action there, but then, it's gone already. If you have an action and you have a set of Cauchy surfaces, then of course you can go to a Hamiltonian formulation. You just use the usual ADM formalism. You can get an effective field theory Hamiltonian, And then the statement here, which will generate time evolution along nice slices, and you would find that minus I, or maybe it's even an I, d by t nice slice on some state is going to be the Hamiltonian nice slice on some state. And near the black hole, this guy is time dependent. The Hamiltonian density is time dependent. And you get particle production. And you can estimate where this energy of these guys is going to be something like m Planck squared over capital M. So in natural units, it's the curvature scale, which is 1 over m, that's going to come in. So these are the Hawking particles in this picture. So there will be particle production simply because this is not generated by symmetry, this Hamiltonian evolution. Now, this is not a practical way to get the thermal spectrum, that's obvious. On the other hand, it is manifest in here. This is an effective theory that has a cutoff built in, so there will be no Transplanckian modes here. So if you could actually get this to work, you would have a way to see that you get the Hawking effect without ever having any Transplanckian modes. Remember, in the computation I did yesterday, we had this niggling worry that these modes that we were using in the intermediate steps, they were actually enormously highly blue shifted as we traced them back along the horizon. So clearly that is not the case here. And the closest thing to this construction is this infalling lattice model of Corley and Jacobson, where they actually manifestly have a cutoff, and they actually do see particle production near the horizon. So that is, but that theory actually is not very good at describing things that are far away from the black hole. The Goldstrand-Padleve coordinates are kind of degenerate as you go far away. So you want your nice slices to cover both this region close to the horizon, but also be good slices far away. And they should actually be things that asymptotic observers, inertial observers far from the black hole, should be happy to use. And they are, of course, because asymptotically, this time variable is just the Schwarzschild time. All right. Now, this classical construction, of course, you can let these slices be. You can let t be whatever you want, right? So they can go on forever. This diagram actually is kind of, you can just keep going here. And I don't know if any of you have actually done calculations of holographic complexity. Slices are actually exactly the sort of extremal volume surfaces they come up in those computations. And it's the same thing there. Those actually would allow the complexity to grow forever. And you expect semi-classical effects. In this case, of course, when you really do it for a black hole like this, you cannot have them grow forever, because as you let them, when you do the construction here, you will eventually run up against this. So you'll get a finite length of time that you can use them. But you can use them actually, you can construct them for a time that is actually, parametrically the lifetime of the black hole. If you have a very large black hole, for most of the lifetime of the black hole, this region, you can safely go through it. And it's not until the black hole is getting, close to the Planck scale that you would worry about. So there will be a finite but very long time that you can use this, and that is kind of, and you expect them to, maybe not for the full lifetime of the black hole, but they will, for example, be perfectly good past what's called the page time, which is when half the area of the black hole is gone. So you can certainly you expect to have a construction that works for that. And the main point of this is that any formulation of the Hawking information paradox, which is what I'm going to talk about tomorrow, it implicitly assumes that you have done some sort of slicing like this. It assumes that you have a local effective field theory, which has the feature that you can have a single time slice where the infalling observers and infalling stuff are at low energy. That's what I just said before. And yet on that same slice, so those actually will look much more like this. And this is maybe not, you will have slices that do something like this. So they'll capture most of the Hawking radiation. So you'll have a single time slice where there's an awful lot of Hawking radiation that's going out, right? And on the same time slice, you can talk about things that are still falling in. This is counterintuitive, but you can actually do this. And that's always an assumption that goes into those discussions. So that's where we'll go tomorrow. We'll talk about the information problem, and sort of I'll comment on to what extent we are relying on these kind of constructions. Yes. Well, no, but the black hole doesn't go away here. Very late time slices in this diagram are of course up here. And there's no black hole anymore, right? And since we're labeling things by the Schwarzschild time out here, roughly speaking, these time slices are at time. You compare to the time when you first enter here, down here, right? They're going to be of order the black hole lifetime later or more. Right. It's because that's not a semi-classical, this is a classical black hole. So the semi-classical black hole has a finite lifetime, this one doesn't. So that's the difference. This is just so much easier to draw than and actually put numbers to. But of course, for a very long time, this is a very good approximation. Okay. You get to put t over, t gets to be of order m cubed. So this is e to the m squared in Planck units. That's a very, very large number. Okay. Which? Because they don't allow you to talk about things that happen inside the black hole. Oh, you want to do it in Kruskal coordinates? Yeah, well, Kruskal time, actually, you hit the singularity. So you need to also avoid the singularity. So, look, we're trying to have our cookie and eat it. And we can for a while, but eventually. Okay, well, let's continue tomorrow. Yeah, sorry, we're a bit over time here.